And this presentation is about, you've guessed it, stages of compilation. What happens when we compile? And as you can see down the bottom here, it says that you've got to describe the principal stages involved in the compilation process, and then it goes on and gives you a list of what those are. So when you compile a program, we have to go through these stages here. So we do lexical analysis, and then that involves a symbol table construction. And once you've done that, we do this thing called system syntax analysis. And once you've done that, we do a thing called semantic analysis. And then once you've done that, we do code generation. And that code generation may involve optimization. And this is a kind of really fun process. It's quite, what should we say? It's quite involved. And you can probably guess from it has to kind of make several passes through the program to do this. And it's one of the reasons why compilation takes a while. And it's one of the reasons why compilation is a very, very complicated process. I'd say if you look at the complexity of systems, compilers, it's right up there with anything else that is ever done in computer science. So the objective of all compilation is that we're going to take source code and we're going to turn that into object code. So object code is machine code, but it may not be runnable on the machine at this stage. So we write our code statements, and the object code, as I say, it's executable code, but it may not be immediately executable. We may need to do something to it before we can execute it. And I'm going to use C++ as the kind of example here, because Visual Basic and C# don't compile in the standard kind of sense that other compiled languages do. So C++ does. So we'll look at that. So yeah, if we go through that process, source code all the way through to object code. Now, you've got 4 stages. You've got lexical, syntax, semantic, and semantic analysis. And then we've got this code generation at the end, which can include optimization. Optimization isn't necessary, but all the other 4 stages are. And they have to be done in this order. And the output from one stage then provides input for the next, and so on. And what happens during compilation is we run through each stage, and if each stage completes, we move on to the next one. And if it doesn't, we kick out all the errors we've generated up to that point. So there can be a lot of errors caused by a very small problem. You get these spurious errors that appear all over the place in your program. It kind of look like you've made a big mess of it when you kind of missed out the close of a comment or something like that. So step 1 is lexical analysis. Excuse me. And the first thing we're going to do is we're going to take our program and we're going to strip out all the comments and all the white space. So we end up with just computer code at this point. Then we're going to read through that, and we're going to use some code statements to check that the variable names are correct, are valid, as in, for example, it's a variable name, does it start with a number? We're going to go through them all, so we're going to go through and we're going to take all the keywords that we can identify. And as it says here, keywords, constants, and identifiers. They're most of these binary tokens. So first of all, we would read through the code program and take all of the keywords in the language and replace them with a standard binary token, which is just a standard straightforward lookup. Once we've done that, and when I say keywords, we'll also replace all of the symbols. So if you see a bracket, an assignment, anything like that, there's a token for it, it'll be put in. So that, therefore, what we have left is stuff that the developer has kind of come up with. So it's either a variable name or a constant, or it's some kind of other identifier the developers put in their program. And what we'll then do is we will give each of those a binary token, and we'll use that same binary token for that identifier, constant, whatever it is, throughout the whole of the program. And we put these into a thing called a symbol table. So as it says here, you've got a symbol table, and in there it will have the all of the user-defined items. It'll have the tokens for all those user-defined items, and it will also have put in some information about data types into there. So it kind of needs to know what kind of data this is and what it's been defined as. And if there's any problems, we'll kick out an error report at this stage. So that's lexical analysis stage 1. Now, what we've got is as it says down here, a token stream. So at this point, the program has been turned into binary formats, but we're not done yet. So step 1, get rid of all of the junk that the computer doesn't use, the white space and so forth. Replace all your keywords with binary tokens, and then take whatever's left and use that to build a symbol table and give each of the user-defined items a binary token. Now, we use these kind of tables. So if you look at this piece of code here, so we've got a simple piece of code, a relatively simple piece of code. What we're going to do is each of the items in that code that are parts of the computer language will have been given a token. I've shown you them here in hexadecimal, but the reality is they would really be in binary, of course. And you'll notice symbols are included. So we could take that code on the left and we could replace it with all the tokens on the right. So the first line would say, for example, 4C score, and then on the next line it would say 4D score, 4E, 4F, and then on line 3 it would say score 50, score 51, and then it would have the hexadecimal equivalent of the number 20, and so on. So what is then left is the identifiers, and this is where we're going to take each identifier and put that into a table. So here's this code. Here's our identifier. So we've gone through and I put in the identifiers, and we've also identified the data types. Now, in some languages, in most languages, you have to define data types. In most compiled languages, certainly you do in C++, our example. In some languages, data types are implicit, so the system simply works it out from the assignments that are being made, and in that case it will just basically it will come up with a data type and they'll put it into the table. So in this case, this would have been replaced with a hex token from the previous page, and what we're going to do now is replace this item here. Base cost is going to get replaced with the token 6A. And on the next line, it's going to say 6B, token for the equal sign, 6A, multiplication token, and then the token for, or the hexadecimal value for 0.2. And the little table we're looking at right here and the one we were looking at on the previous page, together they form the symbol table for the program. So what we're going to do is we've got our output, our piece of code here. So there's our symbol table on the right hand side. And what's going to happen is this line of code that we're looking at right here is going to get replaced with these tokens right here. And there's the token stream that we can then feed into the next stage of compilation, which is syntax analysis. So the first thing to just remember, of course, is what is syntax, and syntax is the rules for arranging items in the language. In other words, the rules of the language. So we can define these using various techniques. We've spoken about, or I've mentioned before, BNF, Backus and R form. I might have mentioned syntax diagrams. We're going to look at those later, but you can use these to define the language. And once we've got those defined, we can then use those definitions to go and check the statements that we've got. Now, bear in mind that although it's checking in binary format, it's a computer, that's the way it does it. We could check this in, a human could check this in text format, and it wouldn't really make a lot of difference as to the end result. So what we do is we parse the statements, and notice the R, please. This is the process of taking a line of input, I'm going to say input, and going along that and breaking it up into individual pieces or chunks of data that we can then check or look at. And what we're going to do, as I say, it's going to parse each statement. So it's going to identify, so in the case of a C program, it's going to start at the beginning of the line. It's going to scan forward until it gets to a semicolon, end of statement, identifier, and then it's going to take everything in the line up to the end of statement identifier, and it's going to check that against the syntax rules that it's got. It gets quite complicated because you can have, of course, statements within statements. So it has to have mechanisms for kind of going down to the lowest level of statement possible, pulling that out, checking that, and then putting that in inside the other statement and checking that, and so on. So this is where life starts to get incredibly complicated if you're developing a compiler. So we check the statements against, as it says, BNF style statements. So we've got them, they're all coded into the compilers, and we'll just be able to check all the rule statements against those. If we've got any messages, we would put those onto our errors. We'll produce those and stop. Otherwise, we go on to semantic analysis. Now, semantic analysis, if semantics is all about meaning. So here we're actually looking at the statements and saying, is this statement meaningful to the computer? So we're going to check. We can check them against the syntax of the language, and then we can actually look at, okay, is this statement sensible? So, for example, in this case, one of the things that will happen here is we'll check scope of variables and make sure that the variable is within scope, and it's also the right data type. So as it says here, for example, you can't put a real number into an integer, you can't add a string to a real, or you can't multiply a boolean by an integer, those kind of things. So we'll check those kind of rules aren't being broken, and if they are, we'll get error messages and so on. We're also going to check assignments, and as it says here, can we store these things? So again, this is basically type conversion errors. So this is where we would identify you can't do that, or maybe that statement is malformed and the wrong way round, that kind of thing. Now, once we've got this, we can then go and start to, so we've got a stream of hexadecimal code, binary code at this point. We've checked it, it complies with the rules of the language, it makes sense. We can now turn that into code. And as it says here, this is where it produces the object code. And what will happen is it will use standardized structures or standard structures, and it will replace a code statement with that. So if you remember from when we talked about assembler code back in year 12, you can write assembler code to do the equivalent of a loop operation, and you could kind of come up with a standard piece of code that does that. And effectively, that's what happens. It says, okay, I can see a for loop here, so here's the assembly equivalent of that, or should I say, here's the machine code equivalent of that, and so on. Now, once we've done this, we have machine code that can be executed. I should point out here on the right-hand side, I've got a little picture, and on the right here, we've got some C++ code, and on the left, we've got what that compiles to in terms of assembler. Now, the code generation does not produce assembler, it produces binary machine code. But the kind of point here I'm trying to make is, you can see we've got more lines on the left than we have on the right. So we've got quite a few lines of code here. And on the right hand side, for this simple if statement, we've basically got an if statement and you've got return. On the left here, we've got all of this code here, and that's the equivalent of that if statement and that return. So there can be quite a bit of code involved, but we'll move on. Now, once you've got your, once you've kind of generated your machine code, you do have a program that can run, and that could be run, but we often optimize it. And I'll be honest, most compilers will optimize. So as it says here, the idea is that we want super efficient code. Now, the problem with that is that what your definition of efficiency is. So as it says here, first of all, we want to make sure the program works. And when we finish code generation, we've got code that will work. It might not work very fast or very well, but it will work. So what we then want to do is we want to make sure that we want it to run fast. But we also don't want it to overload the machine, and we want it to not delay the compilation process. The other kind of thing is that we might want to make the program as small as possible, so it reduces like memory footprint and so on. Now, generally speaking, we will tell you, or we will always tell you, to use structured structured programming techniques and use, like, for example, function calls and stuff, and repeatedly call the same functions if you, rather than having multiple copies of code that are identical. If you were to write a program and you were to write it in a monolithic kind of fashion, so instead of having like 5 function calls, you actually had 5 copies of the function. Well, and you did some experiments, you would actually find that a program written in a monolithic fashion runs very slightly faster than one that's written with multiple function calls. And that's because of all the machine overheads involved in doing a function call. If you remember, what happens whenever you do call a function is you have to take the return address and various other pieces of data, you put them onto the stack, you then call the function, that will then add its own data to the stack. So the stack grows, and then when the function call exits, it returns back to the point of invocation, and that data gets popped off the stack. And as a result of this, the stack's getting quite a lot of exercise. Now, there's an overhead in doing that, and if you're doing a lot of that, then it can be it can start to get noticeable. So what the optimizer may choose to do is it may choose to include multiple copies of the same code in the executable, because that will make it run faster. But the problem is then, of course, the executable gets larger because you've got more than one copy of this code. If, on the other hand, you're optimizing for space, you may do the exact opposite, and you may actually try to replace code with stuff that takes up less space but runs slightly slower. So there is a trade-off in this process of optimization, and there's no kind of one-size-fits-all solution that we can go with. So the other kind of factor we need to consider is portability. And as it says here, most languages produce an executable that's targeted at a particular platform. So if you've got a .exe file, it will only that was created on a Windows machine, it's only going to run on a Windows machine, on a Windows platform. So the code is not portable. That should say not here. Sorry, I'm slightly out of line. But yeah, you can't take these binaries off one machine and put them on another. And if you want to put it on another platform, you need to recompile it. And if you've got, even if it's written in, if you, for example, look at Visual Studio for Mac, Visual Studio for Windows, they are different systems and they produce different binaries, and they're not compatible. Now, you may find certain languages, so the C language, as in C with no minuses, no sharps after it, no C++, no sharps afterwards. The C language, there is an ANSI version of it, the American National Standards Institution. And if you go into your C compiler and it supports this option, you can set a flag, and that will force you to code it in ANSI standard, using ANSI standard code only, which means certain things that you might want to do, you won't be allowed to do. But what that means is that the source code is now portable, so you can take it off that machine, put it onto another machine that's got it that conforms to ANSI standard, and you will be able to compile it there. So this may allow you to take your source code off one machine and recompile it elsewhere, and it will work. But to be honest, that isn't very common. And if we want software that can run across platforms, we tend to use different languages, like Java, for example. So as it says down there, Java, what that does is when you run a Java program. So this here is my Java program. The Java program generates what is known as bytecode. Now, Java bytecode, so you write your Java source, it will you then generate your Java bytecode. Now, this is code that has been compiled, as it says here, for a virtual machine. So in other words, a theoretical non-existent CPU. And what then happens is, on your machine, you install a thing called a Java virtual machine, a JVM. And this is an interpreter, and it takes the bytecode that you generated, and it then runs that, translates it, and then it makes calls to the CPU, your particular CPU. Now, what this means is that as long as your computer has a Java virtual machine installed on it, it can run any Java program. So you can take a Java program off your Android phone and install it on your supercomputer, and it will run fine if you've got a JVM. And to be honest, this is the approach that Visual Studio uses when you generate, when you're generating either VB or C# code. When you're doing C++, it compiles directly to a .exe file, which is a bit different. But yeah, this does give you a little bit of portability. And Java is one of these that was as a write once, run many times, a worm, or it's a run anywhere kind of language. So there you go. You will, if you got a file that ends .java, you've got source code. If it will probably end with the .class. If it's a bytecode, and then you distribute your bytecode, and you can then run that on your CPU. And this is doing effectively, it's generating code that is similar to machine code, but it's not really machine code because it doesn't know the specific CPU call that it's going to have to do at runtime. That is known in this. That's defined in this JVM down here. Right. So after we've compiled, we've got an object program. So back in the time when I used to write code, I worked on Unix machines. So we would write C programs, and you would edit these using a text editor. On a Unix machine, you might use a thing called Vi, for example, VI. Which is a lovely editor, or if you're a masochist, that is. If you were kind of did a lot of coding, you'd probably develop using some kind of a slightly better editor than Vi, like you might use Emacs, for example. But once you've compiled your program, you would save it, and it would be called something like, I don't know, I'm going to call it program.c. So it's just a text file at this stage. What you then do is you run the C compiler, which is called on Unix is called CC, and you would run a CC command. Normally, I'm going to try and write this out, but I'm writing with a mouse, which is quite awkward. You would type in, for example, CC pro.c, and then you have an output. And I'm going to have we're going to output that to a .obj file. So that tells the computer, I want to compile my program. This is my source, and this is what you're going to generate. So at this point, we have an object file. And what we then have to do is we take this object file and we use a program called link. And we're going to take my program plus a load of other ones. And that's going to generate a program called pro, hopefully, which will be my my final program. On Unix machines, we don't have to have the .exe extension. You can just have a file name, and that can be executable. Now the thing is, when you press the start button on Visual Studio, it effectively does all of that for you. So you never actually see this thing happening, but linking is happening still. So linking happens after we've compiled. It's as I say, in the environment I used to work in, it was a standalone process that you had to do yourself. There's a script, a thing you could use called make, which will kind of run all of these for you, but you have to write a script that drives make. So effectively, it doesn't really save you a lot of time. But the idea here is linking is all about this thing here, which is we're going to take pre-compiled modules and combine them with the code that we've just generated to produce the executable program. And as it says here, your program might be using libraries of code, and it might need to link those into your program. So I was hoping I've got a little example there. So in a C program, for example, you will often see at the top of the program, again, I'm going to have to kind of try and draw this with the mouse, which is a bit harder than typing it. You would see a statement that will say something like hash include. I'm not going to write the word include out in full. And then you'd have std.io, standard input and output. So this is a library that contains all of the modules that are used to read and write, do basic reading and writing to either the screen or to files. Now, one of the things that you would have to do when you link in is this is going to be one of these standard libraries that you're going to have to link in. Let's say as well you've done some, I don't know, some maths on the machines I used to work on. There used to be a library called math.io. I always wanted to put an S in it, but you know, can't get everything, can you? And again, that would be another library that we would need to link in. There was one called Oracle. There was one called Oracle.h. We'd have to put that in if we're going to go and talk to a database and so on. So the idea is it's taking your object code that other people have made, and building that together to create your program. So you then end up with an executable program, and then if you take an executable program apart, generally speaking, what you've got is at the one end of it, you've got something that is analogous to a symbol table. So it's basically got a list of the variables the program uses, constants, all that kind of stuff. And then you've got a big lump of code down here, which the program's going to run. And then there'll be an entry point right here, which says this is where you start running when you run this program. So what happens is when you want to load it, and you type in the program name, it starts to load into memory. Or in the old days when I used to run BBC microcomputers, we used to type in run and then the name of the program. We're going to go off and find some memory. Check we've got enough memory. Then we're going to allocate it to the program. Then the operating system is going to go and get the code, or it's going to read it off the back-end store, and it's going to put it into memory. The memory is just allocated. Then it has to map all of the variables to RAM locations. So up here, we've got a big list of all of the variables and that the program's using. We're going to now map these to a physical memory address. And then once we've done that, we can point the program counter at this address here. And at that point, we can then start running away, and we fetch, decode, execute, and all that kind of stuff. And away we go. Every time we then do a swap, so every time the program gets suspended, runs its time slides to an end, and it suspends, it will then have to take all that data, write that out to the swap file if necessary, and then when it reloads, the loader again comes into play because it picks the swapped program up, finds some memory to put it into, and then it'll have to remap the all of the symbols, because we don't know the memory locations we were using are probably being used by someone else now. So we're going to have to shift all of those around, and then we can carry on again. So that's the loading process. Now,